Thanks, Melina, and thanks, Scale, for having me back. This is a great conference, and I hope I've got a good talk. This is about Linux profiling. It's Netflix that was just introduced, and I'm going to be covering two main topics. One is how to get CPU profiling to work and to overcome gotchas. And this is something that most of us in the room, if not all of us, should be able to do, to be able to understand really what the CPUs are doing and why they're burning cycles. The second one is a tour of Perf events and its features. This isn't something that you need to learn how to do exactly, but it's something that is useful to know can be done, so that you can look up the documentation, the slides, and other resources later when you need it. So CPU profiling, how to actually get that working, and then a tour of various other things for when the time comes. As I was introduced, I work at Netflix. We have a massive Amazon EC2 Linux cloud, and we also have some FreeBSD for content delivery. Last year when I gave the keynote at Scale, the primary operating system I was working on was a fork of Solaris called Illumos, and secondarily I was using Linux. This year now the primary operating system I'm working on is Linux, and the secondary operating system is FreeBSD. So I still get to have a little bit of perspective when I'm doing operating system work to see it from a different point of view, which is really fun. Performance for us is critical, so we really do care about understanding exactly what's going on. I don't know if also got the screenshot. House of Cards will be released very soon. House of Cards is released officially very soon, so it should be really good. So that's the agenda. The big part of this talk will be the gotchas, so that you can really get CPU profiling to work. So the first section is why we needed Linux profiling in the first place. At Netflix, we have a lot of instances. Most of them are running Java. We do have some Node.js, and we do have some other things. And if you're in the Java world, there are a lot of profiles out there. There's lots and lots of commercial ones, and it's not too hard to build your own using, say, the JVM-TI interface. And so why do we need Linux profiling in particular? Our primary motivation is simple. It's to understand CPU usage quickly and completely. Quickly, we're building a tool called Vector, which we should be open sourcing along with everything else we open source on Netflix OSS. Vector is a near real-time instance-level observability tool. And so we've got graphs like, here's my CPU utilization per CPU and whatever. If I see a CPU issue, I can click and say, do a perf events-based CPU profile, and then give me a flame graph. And so that's quickly. I see a CPU issue, give me a flame graph right now. And then the flame graph will explain CPU usage completely. So has anyone used or seen flame graphs before? Yes, we have probably more than half the room, which is really good. Flame graphs are a fairly simple visualization for stack profiles of data. What's really special about using Linux as perf events to do profiling is we don't just see inside the JVM, which is what basically all of the other Java profilers do. We get to see everything. We get to see Java, we get to go into the kernel, C code, libjvm. You get to see the complete picture. And there can be issues in other areas which you normally can't see if you're using, say, a specific Java profiler. So it's the only complete picture of CPU consumption. I'll explain it in a bit more detail in another section. Yeah. The value for Netflix, so doing CPU profiling, it's really important for instance response. With the Netflix cloud, we have tens of thousands of instances like I mentioned, and the number one resource that we're scaling for is CPU usage. And so often, as it happens during incidents, there is a CPU usage-related issue that we need to understand quickly. And so being able to quickly understand, not go and use a Java profiler or a Node profiler and only understand just what the application is doing, but understanding everything, because there can be an issue that comes out of a system library or comes out of the kernel. And so we want to quickly and completely understand all of the CPU cycles so that we can make a better direction of attack to fix the issue. Non-regression testing is really useful for CPU profiling. In the Netflix cloud, we have rapid deployment of change, and engineers have the freedom to make changes as quickly as they like. And sometimes CPU usage can regress because of software changes, and being able to easily compare that with perf events and flame graphs is useful as well. and lots of other reasons, like software evaluations, performance tuning targets. It's optimizing our price performance. We have a very large IT spend on the cloud. And like I said, most of the time when we're scaling in the cloud and we're getting into the tens of thousands of instances, it's dictated by CPU usage. So understanding CPU usage, even if we find a near 1 and 2% wins, they end up being very significant savings. So we do care about this a lot. Workload characterization is another reason that we want to do CPU profiling. And this may help you understand what it is we're doing here. With workload characterization, it's a methodology, a performance analysis methodology that's been around for a long time. My take on it is just to summarize it using these 4 keywords: who, why, what, and how. And for CPUs, by the way, workload characterization, it's one of those methodologies you should be able to do for anything. It's really straightforward. And for CPUs, for who, you want to know which process IDs users are consuming CPU. Why is the code path in the context? What CPU instructions you're actually executing and running and cycles, and how is it changing over time? Like I said, this is a basic performance analysis methodology that should be straightforward. Workload characterization solves more issues than anything else, because as it turns out, most of the time you have a performance issue, it's not because you forgot to tune some little thing, it's because you're just doing something dumb. And you just need a means to be able to understand who's eating the CPUs, why we're eating the CPUs, what dump process is running by accident, did someone leave running, what code path has gone haywire that we don't know about. And so it's just understanding what you're asking the CPU to do solves a bulk of the issues. Visually, this is what it looks like. Who, why, how, and what. And for who, it's something that we should all be pretty good at. So running top and htop to understand which processes are using CPU. So no, Java's using CPU, or this process ID. How is also something that a lot of us are really good at. So there's lots and lots of monitoring tools out there that will show how the CPU usage is changing over time. But then it's the other two that people aren't so good at. So why is CPU being used? So Java hits 100%, so it's a common problem for us at Netflix. So why is Java eating 100% CPU or multiple CPUs at once? Do you go and use a Java-based profiler, which might solve the problem, but you might only be looking inside Java? Do you have a system profiler? So this is what Perf events helps us do. And also what? When it comes down to what are the CPUs really doing, what are you asking the CPUs to do? That's, so Perf has that capability as well. So Perf, in terms of CPU workload characterization, not just why we're eating CPUs, but also what we're asking, the instructions and the cycles that the CPUs are performing. Most companies doing performance monitoring today, and people building their own solutions, are really good at the who and the how, but are really bad at the why and the what. Are really bad at, show me, like, here, I know Java is 100% CPU. Why? Like, why exactly? What code paths? Is it in the JVM? Is it in compile? Is it in GC? And it gets tricky. A lot of the time I see people treat applications as a black box. And instead of using a profiler, let's just go and add print statements and dump it to a log and deduce it that way. Or we'll just make assumptions. We know that this code path is hot on CPU, so just time it, add some timers around it, and so on and so on. Profiling will show you what's really happening and why you're really eating CPU cycles. And of course, to understand what the CPUs are really asked to do is helpful as well. So in terms of resetting expectations, doing just top-level metrics, who's eating CPU, who's on CPU, and showing that over time, that was pretty good in the 90s. But today we should really have access to all the information so that we can complete the workload characterization method, and you know all of the reasons why CPUs are being consumed and what they're doing. And also for all the other reasons I mentioned at Netflix. It helps for incident response, it helps for non-regression testing, and so on. So we want we want to easily understand why CPUs are used, a profile, which Perf events can do on Linux, visualized effectively, which frame graphs can do. And this is something that it should be easy to do. So a very important takeaway from this talk is you should be able to do CPU profiling. Perf events on Linux does all sorts of advanced things like dynamic tracing, and you don't necessarily need that until the time comes. But CPU profiling is something that you should be using now, especially in environments where you're dictated by CPU usage, like on the cloud, like on the Netflix cloud. As a recent example at Netflix, and the font size of the plane graph is a bit small, but we had CPU utilization on a Java instance was 100%, and so it was eating one CPU, and then the performance for that instance was terrible, and so we were asked to take a look. The Java profilers couldn't really explain it, so this was a mystery instance, and we had these cropping up within one of the service teams at Netflix. Every so often Java would just flatline at 100% CPU, no explanation. Java profilers couldn't explain it. We were using the vector, which we're still developing, so we got to use vector and run it on it. So there's 4 CPUs, one of them's maxed out, fine. Do a flame graph, and the flame graph shows we're in Java. So I colorize it based on what area of code you're in. Yellow is just for C++. This is just the JVM internals. So as it turns out, Java was 100% CPU, not because it was in Java code, which I colored green. There's actually no Java code running at all. We're stuck in one function. This is a stack trace. And so going down is ancestry. The function is process uses of allocation, which is called by eliminate, allocate node, and so on and so on and so on. So we're just stuck in one function, and that's why we're burning CPU. So that was really helpful because this turns out to be, we believe it's a JVM bug. And I did a code up and registry analysis of that. So, but because we're using perf events, we get the full profile, so we understand. And this, again, this is something that other profilers, if you're just using specific application profilers, we wouldn't have been able to solve this issue. You needed a system profiler to look at the big picture. So I've mentioned perf events a number of times, and as a crash course into perf events, what it is, perf events is the main Linux profiler. It's used with the perf command, and usually it's packaged up like Linux tools common, and then there's a companion package. It's really useful to learn if you're not using perf events already. Who's using perf events already? Actually using perf events? Okay, great. So we have like 10% of people or more. It's in the mainline Linux code, so it is heavily maintained. In the last few releases, there's been lots and lots of changes to perf events improvements. There are lots of traces and performance tools for Linux, but there aren't that many that have made it into mainline, and perf events is one of them. So a big advantage of having it in mainline is it does get maintained, and it's generally very reliable. So it has lots of features like CPU performance monitoring counters, trace points, dynamic tracing, and so on. If you just run the perf command, it will give a list of subcommands. This will make more sense when I show you some one-liners. So perf can list probes, we can record events, report a previous record command, and so on. When you use perf at the command line, it has a... so it behaves like this. In fact, this is... I was just setting up a demo. Let's see if this is going to work. This is a little bit boring because it's on a VirtualBox instance, because I wasn't sure if the network would cooperate. But just seeing it live might just help you understand the sort of process you can use with perf events. So I've got an instance. If I run perf list, these are various probes that are showing up. I don't have many hardware probes because this is a VirtualBox instance, but I still have a lot of software events. If I run the perf command, these are all the subcommands that I can use. And I can do things like perf. Actually, I should start with perf list. Like, you don't have to use grep, but you can use grep. You can just use perf list and then give it an expression. But so there's lots and lots of events that you can instrument and get information from, either dynamically or statically coded trace points, and also hardware events. I've just listed a whole heap which are from ext4. And there's multiple things I could do. One of them is just perf stat. I'll just do that. So perf stat minus e, I'm specifying the event. The event is ext4, all the probes. Minus a means instrument this on all CPUs. And so I hit Control C, and this kind of word wraps in a nasty way, but not much is happening on this idle instance. Let's like, at least do something that might touch the file system. So at least you're reading things. No, it's not touching it. So perf stat. What's interesting about perf stat? So now I've got some things lighting up. So DA write begin, mark I node dirty. What's interesting about perf stat is this is a mode of perf where it's doing in-kernel counts. In-kernel counts are great because they're really efficient, and the performance overhead is fairly low for this. And so generally, if I'm using perf events, I'll start with a perf stat just to get an idea of the rate of events. If I want to know how quickly things are happening, I can give it a command like this. This is actually a dummy command. So I'm running perf stat sleep 5, and so the duration of perf stat is going to be 5 seconds, and so in 5 seconds we did 3,589 of ext4 DA write begin events. So that's just as an example of perf stat. What I really want us to learn, however, is not counting events in the kernel. The main thing to learn is CPU profiling. So looking at the stack traces of why we're consuming CPUs. And so for that, I will use a different mode of perf. And so what I'm going to do is I'm going to record at 99 hertz. So minus F99 means record at 99 hertz, A for all CPUs, and G will record the call graph or stack trace. Perf record operates in a different mode to perf stat. With perf record, we are writing to a file called perf.data, and then I'll go and use commands to post-analyze that. So what I'm going to do is I'm going to give it a little bit of, because my system's idle, but I'll give it something to do. So how about, I'm just going to run date a lot. Font size 16K, how about that? So I've got two things running. I've got a just infinite loop of dates and also urandom. I thought of this like 10 seconds before the talk. Which of these is going to consume more CPU? Well, that's easy. I can just run top, right? Just run top and say, oh, it's DD. DD is consuming far more CPU than the date command, right? Well, we don't really know, because the way top works is it's taking snapshots, and the other command, where I'm doing an infinite loop of short-lived processes, like those date commands aren't here because they're all short-lived, but they could actually be consuming more CPU than DD is. Imagine you're doing a build, like a source code build on a server. All those short-lived processes to do the build, you don't really see them in top. And so, I mean, there's different ways to attack it. Perf events is just one of them. And so perf record. Let's do it for 5 seconds. Actually, let's do it for... So perf record, again, this is writing the perf.data file. These messages it gives you are actually really interesting. It's saying, I woke up this many times, and that's how big it was. It's also in the name of reducing overheads. It is waking up only a finite number of times, and dynamically. So instead of waking up every time there's a sample, that would destroy performance, because all the context switching between kernel and user level. What perf events is doing is dynamically picking a buffer size in the kernel, and then doing the minimum number of context switches to copy that out to user space. So all in the name of improving performance. I can now run perf report. And then this is, I don't actually like perf report very much, but some people do. This is giving me an ncurses-based view for navigating my profile, and I can sort of click around and say, oh, DD was, at least that code path was 41%, and there's other ones here, but I kind of have to add them all up to see who was the winner. There's also perf report. Actually, let's do perf report. If you do -n standard IO, it will do that, but instead of ncursors, you'll just dump it out. And I can also do perf script, which just dumps out all the events. So perf script is I have this perf.data file, which was created by perf record, and now I'm using different ways to look at it. And with perf script, what I like to do is, so I'm just going to dump it to a text file, and then turn it into a flame graph. So the flame graph software is on GitHub. It's just a simple Perl program, and it's just a different way to navigate the performance profiles. So here's a flame graph. The flame graphs are nice because I can mouse over elements and I can zoom in. So DD was 66% of the samples. DD is the winner. So DD from dev urandom is actually consuming more CPU than bash and date. And why was it consuming more CPU? I can navigate around the flame graph. We're in sysread, extract entropy user, extract buff, raw spin, unlock, IIQ restore. Because I'm reading from dev urandom, it's trying to get some entropy to generate all those. Isn't urandom supposed to not do entropy too much? I should have tried dev random to see how worse it was. Anyway, so it is at least going into here to some. I wasn't expecting that much, but you can also click on things. So let's zoom into date. This is what date's doing once it's on CPU. We're in trace sys, and what's nice about the flame graphs is it immediately quantifies the areas of the code path areas. And so as a performance engineer, if I'm saying we're going to eliminate a code path area, we're going to make that vanish, I can calculate speed up. So let's say an engineer says, yeah, we can get rid of this. We can totally get rid of this. It would be totally worth it for the company. You can say, well, it's 2%. It's 2% of samples. So maybe you'll go 2% faster because we've just freed up that headroom. And so quantifying the profile very quickly is really useful, really valuable for a performance engineer. So I'll just pull my laptop notes. So that was a quick live demo. In the slides, I have a tour where I showed the command. And really, there's three components to the command. The action, the event that you're monitoring, and the scope, or instrumenting. Actions, perf stat I did a demo of. That's where you're counting events in kernel for low overhead. And then sampling events, that's perf record. And that's going to write to a perf.data file for post-analysis. And I turned it to a flame graph to make it easier to navigate. And there are various other actions. As a workflow, and I sort of demoed this, I generally start with perf list to have a look at the events I might want to instrument, perf stat to count them, just so that I know. But if I'm going to do a perf record, we're writing all the events to a perf.data file. And so you kind of want to know, is it going to be a 10 million events or 10 events? So what's the rate of those ext4 DA write begin calls? And so I'll start with a perf stat because it's in kernel counters and that's low overhead before I go into perf record and then dump it out. Once you do perf record, you dump it to a file, you can then process it in multiple ways, like flame graphs. The different events we have, so there are different categories, custom timers, hardware events, trace points, and dynamic tracing. I've drawn a map to really help explain their role. So trace points, these are groups. So we've got a group of syscall trace points to instrument the system call interface, other groups to look inside the kernel and see what it's doing, and so on. We've got software events, CPU clock, and these work inside my VBox instance because they're not hardware related. I don't have these in my VBox instance, but if you're on physical hardware, you get to see low-level CPU details on what they're doing. There's also dynamic tracing. So if the trace points don't explain, so if I need to see inside the scheduler or virtual memory, and the trace points don't explain that in enough detail, U probes for user level code and K probes for kernel level code, and that means I can instrument anything. That's dynamic tracing, and it is in the Linux code, so I get to use that. So really with perf events, you can spend a long time just instrumenting and understanding everything. This is part of the talk where I don't want you to know how to do all of this in 60 minutes, but you need to know that it exists. So I want you to know how to do CPU profiling, and I want you to know that that stuff exists. So listing, scope, just so you know what perf can do. Apart from doing, say, system-wide all CPUs, I can point it at a process ID, or I can launch a command. And then for some one-liners, one-liners are a good way to see how the action, the event, and the scope fit together. So here's some example perf stat commands. Normally, if you run perf stat, it'll give you basic counters, but I can say perf stat minus E. I did a live demo of ext4 stuff, but I can say scheduler events. Here's some hardware counters for a command, and so on. Perf stat's nice, like I said, because it's doing in-kernel counts. Profiling events. This is where I'm going to record to a perf.data file. And so here's the similar command I was running. I might want to aim it at a particular process ID and only profile its CPU usage. Or I might want to do the whole system. So instead of -p pid, I can just do -a for all CPUs. And I can also do profiling based on other events. Instead of profiling based on CPU samples, I might say profile based on every 10,000 level 1 data cache misses. Give me a stack trace. And so that way I can understand in my code who's causing memory I/O. And it gives me a different way of different information, which gives me different actionable items if I'm a developer. I know that I'm hot on CPU, not because I'm retiring instructions, but because I'm stalled on memory I/O. So how can I reduce that or improve memory locality? And then reporting, I did some demos of that. So if you've done perf record mode, you've created a perf.data file, there's different ways you can report the contents. All of these slides, by the way, are on SlideShare, and I've put all the one-liners online, so you can play with them later. That's a very quick crash course on perf, but perf can do a lot more. So custom CPU performance monitoring counters to really understand low-level CPU details, dynamic trace points, and so on. But what I really want us to be able to do is CPU profiling. And so CPU profiling this is where you're going to record a stack trace at a timed interval. So like my perf record -f99. Let's say I was calling function A called function B, then blocked, went off CPU. So my stack samples, so there's function A stack, now B's on CPU and A's its ancestor, and I'm taking these samples. Once we're off CPU, perf record is not going to see it if I'm doing CPU sampling. And so it's a coarse, low overhead way just to understand why we're on CPU in terms of the stack trace. I demoed that. One thing I didn't show you on my profile is the output of perf record. So if I did this perf report on a production server that's running complex code, which I was doing here, the full output of perf record is 78,000 lines in that example. This is what a mere 8,000 lines looks like for perf record. And there's the first, you're looking at like a fraction of a percent here. Getting a head around this to answer where are we spending can you imagine like a Netflix incident, and it's like we need to understand where CPU is and like what makes most sense to fix right now. It's really difficult. And also you see the perf incursus interface where you get to navigate interactively is a bit better, but still that exact data as a flame graph is very simple to navigate. And the wider it is, the more samples it was present on CPU. And so you just look for the wide stacks and then address those. So the flame graphs, if you haven't seen them before, I put the code on GitHub, but there are other implementations. The x-axis is just the population sorted alphabetically. So the x-axis is not the passage of time. I'm just showing the wider it is, the more times it was present in a sample. So you just look for the big things. The y-axis is the stack depth. The color for a lot of the flame graphs are random, just to differentiate frames and towers. But I have got some other flame graph modes where I'm using it to identify types of software, and also for non-regression testing, where I highlight in red the code paths that have grown, and blue the code paths that have shrunk as a flame graph. So that's great, and I did demo a flame graph, but when you actually go to use perf events, it turns out things are tricky. I guess the genesis of this talk was I was speaking to someone from another company about perf and Linux and how great it was, and he said, all right, demo profile CPUs right now, I'll watch. And it's like, you want me to demo profiling CPUs? That's trivial. Of course I'll profile. It's like, wait a minute, he's far too smug and happy about this. I sense there is a trap closing. And it's because he'd run into these gotchas before and wanted to watch how I worked around them. So it's like, all right, yes, I need to give a talk where I actually go through the gotchas because they're real. So when you actually go and try to use perf, stacks don't work. They're broken. Symbols don't work, so you profile in Java or Node.js and it's JITed, so there's no symbols. You can't profile them meaningfully at all. PMCs don't work, dynamic tracing function arguments don't work, and so on. So here's my checklist of how I really get started. And that is, step one is you get perf to work. You get the perf command, hit enter, it should work. Then get stack walking to work so that stacks look sensible. Then work on getting symbol translation to work so that stacks have proper names. Then get IPC to work if you want it. Then test perf under load, and you should be good to go for a bulk of the CPU-related issues. So getting perf to work is the easy part, should be, because it's part of the kernel source and there's also packages. The first gotcha is broken stacks, and so this will be pretty obvious. You can just do a simple CPU profile and have a look at it. This is broken, so I'm just running perf report. This is not the, 3 is not the address of a stack frame or a function on the stack. That's just garbage. That's just garbage. These are stacks that are working, right? These look sensible. Okay. This is my the brokenness identification chart. But it does get a bit harder, right? So these are also broken because there's just one sort of set there's nothing else in the stack. It just stops there. This doesn't make sense. These are working. These are good stacks. Even though there's no symbols, they are actually working. And you can see this. Also, these end in the same address, 8AEC5, 8AEC5, which is probably thread start, like we saw in the previous one. libc start main, except in this case, I need to fix symbol translation, but that's a different problem. So anyway, the first gotcha is you want to see this. You want to get stacks to work. You don't want to see this. Getting them to work, here's what it looks like as a flame graph. So you know when stacks are broken because instead of a tower of code, you just get this hair at the bottom instead of what you want. So fixing them there's different ways you can actually generate stacks on Linux. So one way to fix them is to fix the frame pointer-based stack walking, which is its default mode. I like that because it's simple and supports any system stack walker. The cons, it might cost a little bit more CPU to make that available and for the CPUs to keep the frame pointer in use. It's a register. There's another way where you're using libunwind and dwarf info with perf events. More debug info doesn't work on older kernels, and you need to have debug info on the instances, which is a big problem for Netflix because we're creating and destroying instances all the time, and the time it takes to create them is really important, and that's relative to how big they are. So we want the instances to be small, to have a very small footprint. And so adding kernel debug info to instances is a non-starter. There is another way you might do this, and that's where you do a custom walker, but that probably needs kernel support. And I've got experience with them for other profilers, and they can actually cost more CPU when they're in use. They do have an advantage in that they can do better stack walking. They can uninline frames as they're walking, but they are complicated. They're a kernel-based technology, and it can be brittle because they can break because the VM, the Java changes, and so on and so on. So I like the simple approach of just fixing the frame pointer to start with. If it's compiled code, and you compile it with GCC, then -f no emit frame pointer should do the trick. And why we even have this is that a long time ago, x86 had a smaller number of registers. One of those registers is the frame pointer register, which helps debuggers understand where the stack trace is. And so, since x86 had a small number of registers, compiler optimizers, who are the sworn enemy of performance profilers, compiler optimizers decided, you know what? Who needs to debug code? Let's just use that register for our own optimizations, and made life hell for others. So turn that off. I wish this was the default, but that means convincing the compiler optimizers to undo their optimization. If you've compiled code no emit frame pointer, a bunch of makefiles and packages do this because it's annoyed so many people. That's great, but things like Java and Node.js are different. Java has its own compilers. It has multiple compilers inside the JVM. It also does the frame pointer stamping trick where it's going to use that register for something else. And unfortunately, there's no option. There's no -xx no emit frame pointer in the JVM. I was so annoyed at this. In fact, I gave presentations last year where I had the broken flame graphs in Java. I came up with my own hack for Java Hotspot, OpenJDK, and then published it just to show that this was fixable in the JDK. And all I did was, it actually wasn't too hard. All I did was I took RBP, the frame pointer register, out of the eligibility pools for the JVM compilers so that it wouldn't step on it, and also fixed the function prologues so that it initialized the RBP register properly. So the RBP mov RBP RSP. So it wasn't a huge change, and that's been filed as a Java bug, JDK 806, so on. I hope this gets integrated as an option, maybe like -XX more frame pointer. Because at Netflix right now, when we want to do the full nice flame graphs, we have to run Brendan's patched OpenJDK. And we would just rather run like just standard OpenJDK or Oracle JDK. So hopefully we can get that patch landed with an option. That's what broken Java stacks looks like. And see, there's only 2 frames deep. They should go further. That's what a fixed Java stack looks like with my patch. And it goes all the way down to start thread, which is great. These all say unknown because they're missing the symbol. That's okay. That's a separate problem. Like the first notcher is you need to get this to work. And once you got that to work, then go and worry about the symbols. As a flame graph, that's what it looks like without symbols. So the next problem is missing symbols. And so back to the visual identification chart. Okay, obviously in those symbols we've got hex addresses. Now we have symbols. Now for installed packages like installed system software, there's often a debug sim package that you can add and it will give you some symbols. If not, you can recompile from source and run it from there, and you should get symbols. Things get really hard for Java. And Node. Actually, I think it's really hard because Linux made it much, much easier than it could have been. There's some work you have to do for Java and Node.js. There's 2 approaches, really. One is you create a temp perf pid.map file, which has just a symbol translation. Here's the addresses, and here's what the sizes and the symbol names. Very, very simple. Just a plain text file. All you have to do is convince the JVM to spit this thing out. And other people have done it, so there's already an agent you can download which will do that for you and will spit out the text file of mappings. Perf is done. Perf just looks in temp. Every time it knows it's missing symbols, it will just look in temp and see if that file exists. And it's telling you. It's like, so here I'm running perf script that says, hey, I failed to open the map file, so I'm going to continue without symbols. That should be a reminder. It's like, yeah, I can fix that. I can give you a map file. And so also when it's doing simple translation, it mentions it. So the temp map file is nice and simple. In Java, we're using this perf map agent, which is on GitHub. It attaches to a JVM instance on demand and just dumps the map file. A disadvantage of this is it just does one snapshot. If you then do a profile for 60 seconds, symbols could slide during the 60 seconds. And so it can get slightly out of date. I haven't found it to be a big problem yet. And if it was a big problem, I would do a before and after snapshot around the profile and then just diff them to see if symbols moved. There is another approach that's being developed, and it's being mentioned on Linux kernel mailing list right now, and that's where it is a Java agent that will do continual symbol dumps into perf that go into the perf.data file, timestamped. So that's great because you fix the stale symbol problem because you always have a timestamped notion of which symbols were compiled when. It is more complicated. It means the agent needs to be running from boot time. I prefer my on-demand approach. So Java, we're using that. Node.js, since version 11.13, V8 added perf basic prof, which does the same thing. It gives us the /temp translation file. And then, voila, we get the beautiful flame graph, which has, this is the Java code we're running. This is the libc code and lib whatever and JVM. And here's the kernel code. And you have all of the context. So you can properly understand, why am I getting into the kernel there? Here's my Java code, and that explains why. And so that's what this is a flame graph with the Java palette, which just highlights that. One thing to know about that is with inlining, that flame graph is actually, since I'm using perf events, I'm just fixing the frame pointer. This is not all of the real frames or function calls in Java, because the JVM has inlined some functions. if you switch off inlining, things get much, much taller, but also Java runs much, much slower. I haven't found switching off inlining to be that necessary because this still makes enough sense. Like we've solved problems with this, and we know that things are inlined, and there's going to be some things missing, but we still get the overall pattern. As an investigation, I tried, because the JVM lets you tune this stuff, so I tried saying, let's relax inlining a bit. Don't inline so aggressively, just give me a few more frames of context. And Java ran faster. So it's like, this is not why I was doing this exercise. I was doing this exercise to make debuggability better. So now I've got two problems. So I analyzed that to find out why that was happening, and that was happening because inlining is so aggressive. What it's doing is it's inflating out the compiled instruction size, and that's busting the level 1 instruction cache and other hardware caches. And so by doing a little bit less inlining, it's basically reducing duplicate compiled instructions, and the CPU hardware caches work a little bit better. So I was getting 5% for some benchmarks just by not inlining so aggressively. Node.js stacks and symbols covered previously on the Netflix Tech blog, and that's been very helpful for us as well. Same principle. Want to understand everywhere the CPU goes, full stacks, symbols. Another gotcha I want to mention is guest PMCs. So if you run perf stat in its default mode without any events, it will just go and pick a bunch of useful hardware counters like stalled cycles, instructions, and so on. That doesn't work within a Zen guest because the hypervisor doesn't expose the PMCs yet. It could, doesn't yet. And without PMCs, %CPU is kind of ambiguous. So we know how we got there. We have the code path. We know who it is. We know it's Java. We know how it's changing over time. But we're missing the last bits. We're missing what are the cycles actually doing? What's the instruction per cycle, which is a great metric for understanding how fast the CPUs, or how effective the CPUs are. Cache hits and misses and so on and so on. It should be fixable. I need to email some people and encourage them to give me at least these 2 PMCs inside Zen guests. In the meantime, I've actually discovered something else called MSRs for model-specific registers, which happen to be exposed in Zen guests by default. And so they're not as extensive as PMCs, but I can do things like figure out turbo boost. So I've made a little bit of progress with MSRs. Another gotcha is instruction profile. This is a loop. It's a NOP loop, 16 NOPs. NOP is the instruction for no op. It does nothing. We just do 16 NOPs, then we jump to the start. Let's profile it to see which NOPs are hot. That would be the stupidest thing ever. This is like crazy, but there's a reason I was doing this. So plotting the number of samples versus instruction offset, would it look even? So like, doesn't matter which instruction, it's just, we just keep going through the loop and everything is going to look even. Or might there be a different pattern, right? And so, so the x-axis is the instruction offset and the y-axis is the number of samples. That's what the code looks like. Hands up if you think it's going to be A. It's just going to be even. Like, we're just doing a loop. We're hitting the instructions once. No. What about B? For some reason, it's going to be like a normal distribution. Ah, good. I've started getting some people, one person. What about C, where it's like I just, oh, wow. So we have like, now people are getting interested. Now we've got like 5, 6 people saying C. What about D? Now we get much more people. So we have like 20 people say C. I thought it'd be D actually, because these instructions are NOPs, they're cheap. That's the push and the mov and the jump, and they're more expensive. It's going to be D. But the people who picked C were right. I think you'd have done this before, but that's the percent of samples that we saw for these instructions. And we just don't even see some instructions. This is summarizing millions of samples. And we just don't see them at all. And this is just crazy. And the reason why, that's the end of my talk. The reason why I don't fully understand this, but I've been talking to actually, I first learned about this last year from Andy Clean, an Intel engineer, and there's lots of reasons why actual instruction profiling is difficult nowadays. And Intel one reason is SCID, where the time from the interrupt to measuring the program counter or the instruction pointer, the instruction pointer can move by the time the interrupt reads it from CPU. And another reason is we're doing parallel, out-of-order execution of micro-ops. And so this is what I think is the dominating factor, is what happens is we're decoding, because CPUs these days, the prefetch instruction decode pipeline does multiple instructions at the same time. And so this is a 4-wide processor. We pull off 4 instructions, we decode them, we send them down to micro-ops. We set the instruction pointer to the resumption instruction. That's the guy that gets sampled. You can't see these guys executing, just because of the nature of the way we're sampling the instruction pointer. That's the real reason. Intel came up with a hardware feature called PEBs, which can help precise event-based sampling, and Perf has support for it. And you can do things like my event is cycles : pp, and the more p's you specify, the better it is. So this is from the documentation, but putting this into English, if you put no p's, you're saying the sample instruction pointer can have arbitrary skip. So what you're saying is, it's okay to lie, I don't care. And that's the default. Go ahead and lie, I don't even care. I didn't care that you're going to lie. The next one is, it must have constant skip. So that's where you're saying, it's okay to lie, just so long as you're consistent when you lie. And then it's requested to have 0 skid, so it's like, you know what, lying's not cool anymore. Try to tell me the right instruction, but I understand you might get it wrong. And then if you put 3 p's, you're saying, no, you must be able to tell me the right instruction. So whether you can use 1 or 3 or 2 p's depends on hardware support. So I've never seen the full 3 p's actually work. But I thought it was quite an interesting interface. The last culture I want to mention is overhead, and that is overhead is relative to the rate of events instrumented, and that's why I start with a perf stat, just to understand how frequent they are before a perf record. You can also use filter to cut down in kernel before exporting it to user level. The last topic is tracing, and this is where it's more of a tour so that you understand what else can be done. So I've gone through a crash course, CPU profiling, and then gotchas. And at that point, you should be able to go through the slide deck and do CPU profiling yourself. But I also want to mention some other features just as a quick tour. Profiling versus tracing. Profiling is where we just take samples and then we have a coarse but useful view of what's going on. Tracing, generally when we say tracing, we mean capture every single event. And I've got a stack, so perf is the front-end command. It's using perf events framework, and there's trace points, kprobes, and uprobes. But there's other frameworks as well, like ftrace and eBPF. As a tracing example, that's what it looks like to trace. So perf would might see some block I/O event on old CPU, some perf script will dump it out. And I've annotated it there with what all these fields mean. The most mysterious field is the last one. This is called a format string, which is pretty much undocumented, except for kernel source code. That's documentation, right? So you can find it in the kernel source code to find out what the format string means, so what each of the members are. With perf tracing, you get so much data, sometimes it's helpful to visualize it. So here's an example of taking block I/O or disk latency and showing it as a heat map. And so here I've got SSDs, which are fast I/O, latencies on the y-axis. Mostly they're quick, but here's some queuing. And here's some disk I/O. There's 2 modes. There's a higher mode, a lower mode, just random. So just a very effective way to consume a ton of trace data as well. And I've got a URL for how you can build those. And just as a tour of these features, I've got a bunch of one-liners like static tracing. So anything you see in perf list, I can record to a file. So context switches with stack traces to see why we left CPU, syscalls, block I/O. And here's some really good examples of using a filter. So I'm saying, when block I/O completes, only if the number of sectors is greater than 200. Or, when block I/O completes, only if this weird thing, RWBF, which is the flag field, is equal to WS, which is synchronous writes. Or only if it matches that string. So the filters are interesting if you do this a lot because it gives you a chance to filter in kernel before you're dumping everything to disk, so you get to reduce overhead. They operate using Boolean expressions and these variables. And of course, where do the variables come from? I'm not sure that's fully documented, but you can ask the kernel the ftrace interface. So if you can't, there's my trace point, but this time I'm getting it from ftrace, and it kind of gives you this summary. There's all the fields that I can use in format strings to do filtering. So that's kind of just giving you the answer to a very interesting puzzle. I feel like, how do I use this interface? And so I've got other examples of dynamic tracing. This time I can say, create a probe point for TCP send message. And I can do things like, there's the return probe. I can trace individual lines and also members, field members, so long as I have kernel debug info. To Netflix, we often do. So Perf events is really capable. I can go and do dynamic tracing as well. And I've got some advanced examples here where I'm actually walking through kernel structs. So we can't use the advanced stuff very much at Netflix, this stuff, because you need kernel debug info so that Perf knows how to walk kernel structs. We can use this stuff because registers work. And so I've been coming up with ways to map them with a Rosetta Stone of registers, and that's where on one system, I have, on the Netflix cloud, I have kernel debug info installed, which is huge. And I run a perf probe minus nv command, which says don't do it, but be verbose. And perf probe says, oh, okay, if you wanted to trace this whole thing, I would have instrumented CX register as a US64, and then SI, and would have done this and this. It's like, great, there's the answer. I literally copy and paste that with a mouse and go and run that on everything else. And so it's like having cheat code central or something. This is my one system to explain how to do this because it is complicated. And I can go do that everywhere else. It's great. Scripting, just to mention briefly, Perf is a really powerful one-liner tool, but sometimes you're doing things so often you just want to script it and have a tool. And so a few people have done things. Perf does have its own scripting interface. Andy Clean has come up with his own interface on Perf. And it has these great PMC tools if you want to get into low-level hardware counters. And I really love top-down methodology. And I've developed my own, which do things like, this is pretty simple. It's just using in-kernel counters to do the disk I/O size distribution. This stuff, by the way, is really useful when you can look at the distribution. It's really useful if you can do that in kernel context, and you don't have to do a lap via the file system with the perf.data file or through pipes. And so it's tricky to do it in perf events today, but there's workarounds. eBPF, which is being integrated part by part into the kernel, is going to make life so much easier, and basically means we can do everything. eBPF, here's an example of it, where I'm doing a latency heat map, which is printing second after. This is an example from Alexei, the author, last year. Sysdig just implemented this and called it a spectrograph, and used the full color palette, which looks interesting. But what's great about eBPF is it's doing in-kernel counts and histograms. So it's going to basically solve everything else we can do with those tracing interfaces. And it's really interesting to think about the Linux profiling future with eBPF, because I will then be able to do everything. Perf events means I can do a lot right now. eBPF is the final piece. So my summary and your action items is get CPU profiling to work. So maybe if you've got like a, not that I'm forcing this on you, but maybe if you have a work calendar, have a meeting next week and invite my slide deck, and you can go through my slide deck and get this to work. Because it's really useful. I mean, I'm really understanding what the CPUs are doing and why. And then I also just briefly went through a tour of various other things, just so that you knew it existed. PMCs and tracing. And these slides are on SlideShare so that you can browse them later. And I also have a very good list of resources. That's the official documentation for Perf. There's also a mailing list. So if things go really, really badly south, you can ask them instead of emailing me. But Perf is actually pretty good because it is mainline, and so it's been pretty stable for us. And that's my talk. Thank you. There's also, I should mention, my publisher kindly dropped off a book, a copy of my book Systems Performance, and they're downstairs at a booth. That's Pearson. So just as a reminder that maybe I owe them another book or something.
I was curious. I noticed that you had a sample frequency of 99 hertz.
Yes, why 99 hertz?
Yeah, why 99 hertz? Is there special, or was that empirically determined?
It's just made up. It's just so that I don't accidentally sample things in lockstep. because a lot of software, you'll do things at every 10 milliseconds or 100 hertz, and you don't want like constructive and destructive interference, which we heard last night. Yeah, you just want to avoid lockstep when you're sampling. So pick anything, pick 97, 101. Yes?
So in addition to Perf, since you mentioned ftrace, have you used like trace CMD, and how did you compare that against Perf?
So the two mainline traces right now are ftrace and perf events, and perf events they're both really good. And I've also done a whole heap of ftrace work. Ftrace has a front end called trace CMD by Stephen Restat. It's pretty good. It's actually similar to perf events in the way you can dump and then post analyze. I'm not studying trace CMD too much because I think trace CMD is a better example for performance engineers to use. I like to create tools for everyone. So I did the dtrace toolkit earlier, aimed at system administrators, not performance engineers. And so I like to create tools where they just work. And they have a man page, they're really simple, they behave like TCP dump or VMstat or whatever. So I think trace CMD is great if your job is a performance engineer and you're going to be doing a lot of that stuff. I don't use it only because I'm targeting a different audience, I'm targeting more system administrators.
How safe is this to use in production compared to something like dtrace?
How safe is it to use in production? Perf events, a difference with Linux is development does happen in the open, whereas dtrace, by the time it was open, it was already done. Like all the test teams had ironed out the bugs. And so I think some of the Linux technologies get a slightly unfair naming comparison because we have open development and you get to run development versions of things that panic. Now, perf events in particular, it's pretty good. So we've not had any problems at Netflix. It is going to depend on your kernel version. If you Google and search around, you'll see in the distant past, there have been panics with perf events. And so I like to get a test system for a particular kernel version and just try a whole heap of things just to make sure I'm not unlucky before I go and run it on the production instances. I should also say I'm a little bit biased in my answers about reliability, and I need to be aware of it, because in Netflix we're in a fault-tolerant environment, and if I panic an instance, it actually doesn't matter. So I've used system tap in production and panicked an instance, and everything just failed over immediately. So it wasn't actually a big problem. But in terms of perf events, it's for the kernel versions we're using 3.2 and 3.13. It's been great. We've never had a panic.
So you have like hundreds of thousands of instances. Are you picking one and you're doing this on it, or is this something you're doing across a fleet of machines, or is this like a machine, a JVM on that machine, and you're taking a look at it?
Yeah, we have tens of thousands of instances, and at the moment we're just picking them individually just to get a CPU profile. There are things that we want to do that we haven't fully done yet. What I'd like to do is have every instance capture a profile at least once a day, so that if things go bad, you can then have a profile in the good state to compare it to. And so automating this isn't too much work. And I've even automated it at a much more gentle frequency, maybe at just 19 hertz for 60 seconds, just so that I can like spot the difference, do a Pluto blink comparison between the bad state and the previous known to be good state. So, but that's an example of where we'd automate it on all instances, just for the history. Yes?
So you have all these machines, and do you see that the same JVM with the same code is performing differently across the machine? Like, are you finding bugs that are, I mean, at your scale, the edge cases become more common, and so do you find that like the JVM bugs are showing themselves with the same patterns as like your deployment and your hardware and everything else that are like popping out once in a while, but for you it may be like 10 machines or 20 machines?
Yeah, it's a very good point. Since we have tens of thousands of JVM instances running, we hit the edge cases. And so the example flame graph I had where we were stuck in the compiler, it's in an infinite loop. Like that was running for hours, and like I was caught up in it, and it was making no forward progress. That's a bug that currently exists in thousands of other JVM instances running, but they're running just fine. And so it can be really the subtle edge cases that we wear. And so that's why it's really helpful. You see one instance performing badly, and you can understand it quickly.
Okay, so let us all thank Brendan again.